Hey guys, today I'm just going to kind of start from square one with an argument and show how and why we do proofs and the way we do them. So this way I can show you guys a derivation in action. So let's look at this example. Okay, there's three premises in this argument. Okay, my car is out of gas is the first premise. The second premise is my bike tires are flat. The third premise is if my car is out of gas and my bike tires are flat, then I can't go to work. The conclusion, no surprise here, is I can't go to work. So the first thing we want to do is we want to turn this argument into its symbolic form, right? So, I'm going to add 3 dots. That's how you show therefore, so 3 dots. That's how you show a conclusion. So we are going to need 3 different symbols, okay? We have C. Let's say C equals my car is out of gas. B perhaps equals my bike tires are flat. W equals I can get to work. Okay, and if we're going to translate this argument into symbolic form, we're going to do it this way. Okay, first premise is my car is out of gas. So if we want to symbolize the first premise, we can just write C. The second premise is my bike tires are flat. So if I want to symbolize that premise, I just write B. Okay. The next one's a little bit more complicated. It says if my car is out of gas and my bike tires are flat, then I can't go to work. Well, the first part of that is my car is out of gas and my bike tires are flat. So I do a parentheses, and I do C and B, right? But it's not only a conjunction, there's also a conditional in here. It says if my car is out of gas and my tires are flat, then I cannot go to work. So we add the conjunction sign and we say negation W, right? Or I cannot go to work. You put the negation here because W is I can get to work, right? So not W would be the negation of W, right? I cannot get to work. So then what's the conclusion? It's negation W, right? Okay, so let's do a derivation, right? We could do a truth table real quick to show it's valid, but let's do that. Let's do a truth table real quick just to show it's valid, right? And then after that, we can do a proof. If an argument's not valid, you can't do a proof on it. So maybe we'll save some time if we do a truth table and find out that the argument is not valid. It should be pretty obvious that this is in fact a valid argument if you look at it, but let's do it anyways. So we'll start with the truth table and then we'll do the derivation. So first, we have 3 different atomic parts at play. We have C, B, W, right? 3 symbols. So we need 8 rows, right? Just to review, my rows should all be unique, right? I should each have a unique value. And if they each have a unique value, there should be 2 to the power of however many quote variables or atomic sentences do we have, right? So here we have 2 to the power of 3 or 8, and we notice all of these are unique. There's no other possible combinations of these. Okay. Now we put in the premises, right? C, B, and if C and B, then W, not W, sorry. And then finally we have the conclusion, which is the negation of W, right? So for these 2 premises, we literally just copy, right? True, 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 false, 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 true, false, true, false, false, and false, false. Great, okay. Easy enough. Not W. Negation of W is just going to be the reverse of whatever we have for W here, right? So you have false, true, false, true, false, true, false, true. And now we have this row filled for the conclusion. Now let's do this premise. This one's a little trickier, right? So C and B is only ever true. So we'll solve for this first, and then we'll solve for the whole, right? So I'll do it in small letters. C and B is only true, and both of them are true. And so for the lowercase t here, we put a lowercase t here, and then all the other cases are false, right? Now, I don't care about this row, right? This row doesn't tell me anything, except solving for this whole premise. So then we have the negation W. So remember, a conditional is true when... a conditional is false when the antecedent is true and the consequent is false. So this whole conditional is going to be false when when this is true and when not W is false, right? So here in the first row, it's false. Why? Because W is true. So in this case, it is true that my car is out of gas. It is true that my bike tire is flat. But it is true that I can go to work. Well, the whole argument is saying I can't get to work. So then the argument would be false. Who knows, maybe take the train or something. Okay. And the next case here, we have this being true, right? Because here we have the antecedent is true and the consequent is true as well. So the argument is true. All the other cases is true as well. Because when the antecedent is false, a conditional is always true, right? So now we can get rid of this. Okay, we don't care about this anymore. If we want to determine validity, so we look at the argument. Are there any cases where all the premises are true? Here's a case where all the premises are true. Okay, and this is a case where my car's out of gas, my bike tires are flat, and I cannot get to work. Okay? It's the only row where all the premises are true, and it turns out the conclusion is true. So ergo, the argument is valid. Okay? If the argument is valid, that means the conclusion should follow from the premises, and that means I can do a logical deduction. Right? I can prove the argument. Right, so how do I prove the argument? Well, let's start. Right, I want to list the premises. So first premise is C. Second premise is B. Third premise is C and B. Therefore, not W. Right? Okay. So I want to hold off on writing down my conclusion. Right? Because I don't know the conclusion yet. The whole point of a proof is to prove the conclusion from the premises. Okay? So what's the first rule I'm going to use? Well, we want to get C and B. Right? That's the first step. So the first move I make is to make a conjunction out of C and B. Okay? If C is true, and if B is true, that means I know that C and B is true, right? Makes sense. If my mom's in the house and my dad's in the house, then I know my mom and dad are in the house. Okay? But we need to justify that using a logical rule, right? And the logical rule is conjunction introduction, right? There are different names to the rule. Some people call it addition. Some people call it conjunction introduction. There's all sorts of names for these logical rules, but this is the simplest name, right? Just the introduction of a conjunction. So we use the and symbol, right? And an I, obviously, for introduction. Now, what lines do I use? Okay, I use lines 1 and 2 because I have to refer not only to the rule, but to the lines I use to justify the rule. Okay. Now, what can I do? Well, if I notice, okay, now I have C and B, and line 3 says if C and B is true, then not W is true, right? Or if C and B are true, then it's not the case that W is true. So I can add a fifth line that says not W, okay, and I'm using what we call a conditional elimination, right? And so I use E for elimination, and I'm using the lines 4 and 3, right? 3 is the conditional, and 4 is the antecedent that I'm using to eliminate the conditional, right? And the conclusion is the consequent, right? Now, this, right, is the conclusion I was looking for. This means the same thing as this, right? I can't go to work, not W. Therefore, I've used the rules of logical proof to effectively prove my conclusion. Right, these tools really aren't that hard. They're actually surprisingly simple. You just have to figure out how they work. And once you figure out how they work, it's actually really easy to do this, right? So I'm going to be coming out with more videos for the class. Just, pay attention and you'll see them soon. Thank you.